Thank you, Ollie. Wait, I was told my one instruction was not to stand in front of there, but do to pick up that. So yes, so my first instruction to lots of you is please leave, because this is not for you. This is about this equalizing role. So I think you'll find that lots of the material in here might be a little dull, but I'm hoping that it really sets the scene for the next few days, that machine learning is horrible for its jargon. Most of it sort of creates a barrier to people to enter it, but beyond the jargon, the underlying mathematics are not very complicated, and we have found at ECMWF, so I think the start of the AIFS was, which we'll talk about a bit later, was Mihai, myself, and Simon Lang, and Simon only picked up machine learning sort of because all this was happening, because machine learning was entering the field, and is my best showcase for how anyone can enter this field. It's not too late. The jargon is easy to learn. The techniques are manageable to learn, and you can be making some of the most important contributions. So now is the time. Our sort of learning goals are touring through basic language of AI machine learning, neural networks. Mihai's then going to take on for some sort of more advanced neural networks. You can see I've purposefully put in some spelling mistakes, so you can see it wasn't made by ChatGPT. It's definitely not an accident. So you can see that a human has made this. You'll see a few of them, all on purpose, I promise you. And then we're going to talk about one of the recurrent themes that we're going to see throughout the next few days is sort of data-driven weather forecasts. We're going to talk a bit about the history, the methodologies that are there, sort of why it works, and sort of try and set the scene for lots of amazing talks. I feel very privileged to be opening this event because I think the breadth of the science, the speed of the science is highly impressive. And then we're going to finish with some pointers to how you might go about trying this yourself. This might be where you say that this is a bit of a false advertising. I'm not sure tutorial is perhaps the fairest word. We thought about it when Ollie and I were brainstorming what this should be, how much we should aim for an interactive session. And I wasn't really brave enough to realize this in its full form. So we're going to have some QR codes that are going to show you how you can run models yourself, how you can go and look at the guides for training these models yourself, how there's loads of amazing things to pick this up. But we're not going to be needing our laptops. But as you say, given that most of you here know lots about machine learning, you can be on your laptops preparing your presentations or reading about the day's weather sort of news events. So, AI, machine learning, deep learning, these have sort of, this Venn diagram has looked, I think, quite different at different points in time. And increasingly at the moment, the three are highly overlapping with one another in terms of deep learning is consuming most of machine learning, which is consuming most of AI, artificial intelligence. My sort of off-the-cuff line is if people are talking and they're doing science, they talk about machine learning. If there's money involved, they talk about artificial intelligence. We could have some definitions of what it is in terms of intelligence demonstrated by machines, in terms of specific algorithms that are going to use computer systems to learn specific tasks, and then in sort of artificial neural networks based on depth. We are going to be really sort of zooming in and spending our time thinking about deep learning, which is the main thing I would say that is consuming this field. That's not to say that these other areas are not important, just in the interest of giving you a tutorial in just a few hours. I don't see a timer. Should there be a timer that I have? Okay, then you're my timer now, Ollie, sorry. Okay, so similarly, in terms of if this is one sort of question mark about what things we will and won't be talking about, we're going to be talking mostly about deep learning. So then if we talk about the sort of methodology, that is telling us that we're talking about neural networks. So that's one of the places we're going to sort of have a possible branch point and delete it. There are lots of other interesting machine learning techniques that you could be thinking about. There could be decision trees, support vector machines, symbolic regression. Loads of these are really interesting fields. We may touch upon some of them through the days ahead, but the majority of talks you will hear about will be neural networks. And so Mihai and I are going to spend our time talking about neural networks and some related topics about those, because we think we can do the most good in going into the details there. So, types of machine learning. Before we go into types of machine learning, interesting. That's not the slide I was expecting. So first, we can have supervised learning. So that is the process of saying we've got some data. So here we're thinking of different rows are different examples of data, and the different columns are the different sort of things that might be used to make a prediction. So maybe this is the temperature in Zurich, the pressure in Zurich, the wind speed just above Zurich, etc. And then the task is going to be to produce some labels of some kind. So this is the basic of supervised learning. So those labels could be yes, no. Is it raining? Is it not raining? Is there a cloud? Is there no cloud? In which case we're in the process of classification. That can be based on just a singular sort of type of label, or could be a whole zoo of different labels that you're aiming for. Perhaps more common, the thing we're going to hear about more often is sort of regression supervised learning. So here we're aiming for labels that are values, floating point values typically. So that might be predicting the temperature in Zurich tomorrow. It might be predicting many things at once. So temperature, rainfall likelihood, surface pressure, all of these things. And so these are the basics of supervised learning. Another discipline that you're going to hear a little bit about in some of the talks is this idea of unsupervised learning. So what do you do if you are without labels? One example of this could be clustering, which is quite an old technology, but still has lots of value here. So this would be about building an algorithm to figure out how to divide your data into things that have coherence within the data, into subsets that might have coherence within the data. It could be about building a reduced complexity representation of your data, so a dimensionality reduction. These are coming into the fore quite a lot at the moment because we work with such large data sets in weather and climate. So you'll hear things like sort of autoencoder as a way of trying to find a reduced complexity representation of the data by finding a model that tries to compress that data with the goal of reproducing that same data at the far end. And the idea being that this reduced complexity data maybe unpicks a clearer truth, gets rid of some of the correlations that are unnecessary, and finds a sort of minimal representation of your data set that can be used for other downstream tasks. Perhaps the most common set of sort of unsupervised learning at the moment is this idea of self-supervision. One example of this is sort of mass token modeling. So what you do here is you take your data, so this might be space-time cubes of Earth system data, and you deliberately sort of drop some of that. So you might take the weather forecast, the state of the atmosphere over Zurich, maybe over the Sahara, and maybe over the northeast coast of the USA, and you'd sort of delete them from your sample. I'll explain what sample is in a second. And then your task is to fill in those gaps. So you take the data and you're saying, please fill in these gaps. And if you do this with lots of different gaps, so sometimes you drop out different variables, sometimes you drop out different points in space and time, the idea that your model learns all the interrelationships of this data, and it can learn a good underlying representation of how data connects to itself. And you'll see this a bit later when we talk about what's going on in foundation models for weather and climate. So this is this idea of asking the model to then fill in those gaps. So why might we be doing sort of unsupervised machine learning? We might have unlabeled data because labeling needs expertise and is expensive. It might be because labeling can introduce a bias that you don't want to have. And so the pros of sort of unsupervised machine learning is it can sort of exploit the internal structure of data, and you can then accomplish lots of different tasks. So I'm talked about a couple of these, but there's actually a wider set of types of machine learning that are here. So I've explained a bit sort of supervised learning, where we can have classification and regression. Talked about sort of semi-supervised, so I've not talked about semi-supervised, but this is another very interesting problem where you can have partial labels for some of your data sets. And then we've talked also about unsupervised learning, where you can have clustering, dimensionality reduction, or self-supervised learning. Another interesting field is the idea of reinforcement learning. So this might be so learning in an active environment. So this is the technology behind self-driving cars. I don't think any of us in the audience are actively pursuing this field, so I skipped it in the interest of time. So on now to the main sort of body of what I'm going to talk to you about for a few minutes, which is neural networks. What makes a neural network? What are the underlying mathematics of it? And before we do that, I've realized that I already used some jargon without doing it, and my aim here is to do jargon busting. So we're going to start actually with some exploration of data sets and the jargons that surrounds them. So imagine my task is to take, as you will see later on in the concept of data-driven weather forecasting, one state of the Earth system and predict another state of the Earth system slightly further in time. So that's my input, that's my output. If I draw a red box around that combination, is anyone brave enough to say what we might call that, what the jargon might be around that? We're all asleep. I told Ollie that this would happen. Sample, thank you. Let's see if I agreed. Yes, sample, thank you. So that's just one element of your data set, the input mapping to the output. What about if I now grab a few of these samples together, perhaps randomly through the data set? Batch, thank you. You're being my hero. I'll buy you a beer later. Yes, so batch. A batch we'll talk about when we talk about sort of stochastic gradient descent. The core algorithm for training machine learning models is this idea of going through your data set and picking at random, each time going and picking a different small subset of samples, gathering them together and doing this idea of the machine learning algorithm on a different sample of the data set, a different set of batch of the data set. What about if I then go and draw and divide my data set maybe into different big chunks, a large one and a few small ones, sort of perhaps separated in time if I'm trying to make a time forecasting problem? What might I call red? Yes? Validation and then test data. So we're going to talk a bit later about why we might split our data set up to make sure that we can trust the results and build good models. So this is the first of this jargon busting around what we might label what we might call components of the data set that we're training on. So at its basics, a neuron in a neural network is a very simple beast. So here I'm describing a neuron that's going to connect two different inputs to one output. And if I add the mathematics on them, it's a very simple combination. What we do is we have sort of elements that are called weights. There is one for every input coming into my neuron. So in this example, there would be two of them. And I'm going to multiply these weights by the input values. And then I'm going to sum them together. And then I'm going to add on a bias term as an extra degree of freedom within my neuron. So far, that is a linear set of operations. If I compose lots of linear operations, I'm not going to do anything interesting. So the other key component that I need to do is then apply some nonlinear function. And you'd be amazed at how simple these can be in machine learning. So for example, this is a very simple weakly nonlinear function whereby I am 0 for all values less than 0, and I am a linear unit for all values greater than 0, and apply this to the output of this simple linear combination. And that is going to give me my output from my neuron. So here, if we're talking about sort of jargon of the field, so the weights and the biases are the learnable or trainable parameters in my system, and this is what we're going to seek to learn. And this is the basics of a simple neuron. Then effectively, all neural networks is building up large amounts of these in various combinations. So the next sort of hierarchy of this is to go about building a single layer neural network. So this is where I put quite a few of these together, but all next to one another, such that my sort of algebra here turns into more of a sort of matrix. So this becomes a matrix of weights. This was already a vector, and this becomes a vector of biases. And in here, I'm then able to map from a sort of a vector of inputs to a vector of outputs. So that's then a one-layer neural network. But I can go beyond those and comprise many layers back to back to back, such that the output of a certain layer is then the input to the next one. And we use this same combination of the weights of a particular layer, sort of multiply by the values of the previous output. We add a bias of this, and then we apply a nonlinearity, and this will give us the output of the next layer. And then, so what this gives us is a sort of deep neural network, or sort of often called a sort of multi-layer perceptron, which is a horribly overcomplicated jargon for what it actually is. So this block, this sort of MLP, as is often referred to, is sort of a key component of machine learning. And what we're going to see now, sort of throughout the rest of this, is effectively we have just got variations on these multi-layer perceptrons that perhaps have different sort of configurations on how information is communicated. Okay, so what is the training process for this? So how do we actually learn these weights and these biases? So we start with completely random values for these learnable or trainable parameters. So they're going to be terrible because you've literally just drawn them probably from some sort of Gaussian distribution. You're then going to go through this sort of pseudocode where you're going to loop over sort of so-called epochs, another jargon term for you. So this is going to be passes through the training data set. So the number of epochs is the number of times you've seen all the examples in your training data set. And then from within this training data set, you're going to do a loop. So you're going to draw a random batch, a random subset of your training data set. And you're going to, over that set of examples, make a forward pass, apply the model to make some predictions for that batch of inputs. So you'll have a batch of predictions. You're then going to calculate the error, the loss, against the true values that you've got, because here we're going to be, so I should say, we're going to be looking at, so that we're thinking more, or the easiest mental model is to think about supervised learning. And then we're going to take a gradient descent step. So we're going to calculate the gradient of the error with respect to the values using things like the chain rule, and we're going to adjust those values of the trainable parameters to find ones that would reduce the error. And the size of a step that we go is going to be governed by the so-called learning rate, which is another of the sort of the jargon, the parameters that we would want to do. So we're then going to finish through looping through our entire training data set. So we're going to have seen all of the samples in our batch, all of the samples in our training data sets via this batching process. And then we might go away and calculate the loss on our validation data so that we can see if we're continuing to learn something. So often when people talk about this gradient descent, they have some nice example like this of an optimization procedure in a very smooth space where we're thinking about learning in a 2D space, and there are some local maxima, local minima, global minima, but it's relatively easy to go about finding these. I would say in reality, when people try and visualize this sort of lost landscape that you're trying to sort of take this gradient descent through, it tends to look a lot more like this, a lot more complex. And so there are lots of tips and tricks to try and make this look more like this, or in fact have a deliberately noisy and sort of variable step size to try and make sure you don't get stuck in any of these local minima in terms of trying to find these more global minima. So how are we going to define the error? Well, how we define the error will depend obviously on the task. What are we trying to do? For supervised regression tasks, the most common, probably the most common sort of loss that you'll hear is the mean squared error, but there is a really rich zoo of different loss functions. And the key thing to think about with any loss function is, what are we prioritizing? What are we rewarding when we train a specific model with a specific loss function? Because you will get very different behavior. For example, how much to prioritize extremes. So you'll see over the next few days a mixture both of deterministic loss functions, things like the mean squared error, but also a variety of probabilistic loss functions, which I'd say are increasingly becoming popular in the domain. And we're going to touch about that when we talk about what's happening in the field of data-driven weather forecasting. I guess a thing that I'm going to leave for note as we come back to the problem of data-driven weather forecasting later is this statement that in an inherently uncertain problem, which we're typically looking to solve, minimizing the mean squared error will result in a mean prediction, and we will be left with the advantages and disadvantages of that design choice. So, we've talked about parameters. Another jargon you'll hear about will be sort of hyperparameters and tuning. So parameters we've talked about before. They are learnable aspects of your model. So for example, the weights and the biases. The hyperparameters are effectively the settings of the model. So this could be things like, if we go back, sort of how wide this is in terms of how many neurons we aim to have in this model here, how deep the model is, how many layers we put back to back to back to do that. It could be what activation functions we look to use here. It could be the learning rates that we seek to choose. It could even be the loss functions that we seek to use. And this creates a huge design space, a huge decision space for us to be thinking about when building machine learning models. And I would say, I think for the outsider, for the beginner, is probably one of the most daunting things is all of these decisions that you don't know what values to take for them. And I think this is where we sort of have some uncomfortable truths, which is that, to my experience, machine learning, there's some lovely theory underneath it. The reality is a long way away from that theory. And what it ends up being is a very experimental discipline. For small-scale problems, if you have a small enough problem that you can train a model in just a few minutes, you can think about actually brute forcing this space in terms of sort of using a grid search or maybe some sort of more advanced optimization methods to explore this space. However, for larger problems, which many of you are working on already, it's not really computationally feasible to train this. We'll talk about in a few minutes sort of how expensive these models are turning out to be. You can't explore a large dimensional hypercube of these hyperparameters. And so I think what's typically happening, and Mihai's going to talk about this when he talks about sort of more advanced neural networks, is that where possible, people in the field are trying to take design choices from similar problems, similar works, and use those to sort of minimize the design space. So not seek to reset all of these values, but try and find some work where someone's attacked a similar problem and go, okay, so I'm going to use this as the starting place and then explore some deviations to this process in terms of trying to find a better model. That might not work. You may not have an analogy that finds a similar model for a similar problem, but I'd say that's typically how the field is moving most quickly in the space of a huge design, in the challenge of a huge design space. So we might hear about sort of overfitting and data splitting. So when we start building more and more complex models, when we start thinking, oh, well, I could add a few layers, I can make my model wider, I could go to 1 million, 10 million, 1 billion parameters, we can sort of see different behaviors as we train our problems. So we talked about sort of evaluating on a regular basis our validation data. You can see all sorts of behavior if you look at this. So here's a schematic schematic plot of the loss evolving as you do pass through the epochs. And one thing that you can observe is this idea of overfitting. So this is illustrated by this schematic here, where you have learnt a sort of implausibly accurate curve that draws exactly round the dividing between crosses and noughts, but in a way that would struggle to be generalized to a independent set of data. And that's what we're seeing here, is this idea that you are apparently learning something, your training loss is going down epoch to epoch, the model thinks it's getting better, but the validation data is now going up. So the patterns you're finding on this training data are not generalizing to this validation data. So this is where these ideas of training, validation, and test really come out. So training data with data we're directly optimizing on, that's where we're doing these pass-through, this gradient descent operations. Validation data, we're never optimizing over, but we're evaluating on regularly during our training, maybe during our choice of hyperparameters, to try and find out what is the best design for my model. When should I stop training? When should I change the complexity of my model? And then test data is only meant to be assessed once all the design choices are made. So there's no ability to go back and refine and iterate, but say, this is the true unseen behavior of my model that people will be able to trust in a new setting, in a real-time setting. So let's see. About right timing, I'll give myself that. Final messages for this section. And I should have said when talking about sort of learning objectives, don't worry, you're not going to hear from me the whole time. And also we're going to have some comfort breaks for people to stretch their legs, etc. So before we have some opportunities for questions, I want to deliver some sort of final messages around this sort of basics of neural networks. So as we said, we've not really lived up to the full goal of a tutorial, but if you go and look at tools like Keras, tools like PyTorch, you will see that they make building and training these models just incredibly easy. So Mihai is going to introduce in a few minutes the idea of a convolutional neural network. You will see that the ability to put one of these together in something like Keras is really just about 10 lines of code. The ability to train a model to do this complex gradient descent step is 1 or 2 lines of code. Sort of like that bit is wonderfully easy. The bit that ends up taking far more time is actually the data. Unless you're really working on a problem where someone has already curated the data set, built you code for a data pipeline, I would say you can expect to spend far more time on data processing, for example, sort of bringing your data into the same format. You're trying to mix maybe observations and Earth system data, model data, and you want to bring them into a common format. Data cleaning, if you have problems with noisy or missing data, or just data pipelines to mean that you're able to stream lots of data from your disk to your GPU fast enough that you're able to take the most advantage of GPUs. So just to set you up, if this inspires you to go away and do the work, don't expect, sadly, all the time to be spent on machine learning. Expect far more of the time to be spent on this data curation. However, I think it's worth it. I think it's interesting. And I really encourage you to have a go for yourself. So with that, we're going to take our first pause. And are there any questions? Has everyone finished their slides yet? No, I think you have too much expertise, Peter. I'm not sure you're allowed to ask a question.
Interesting too.
You can speak into there.
Hey, Matt. I was pleased to see you show this like classical overfitting plot. I was just wondering, what are your thoughts? How do you reconcile that with like modern deep learning, which basically has thrown this whole idea of overfitting in the trash can, where you have large language models based on a gazillion parameters. How do you reconcile that with this classical statistical idea of less complex models having some merits? Do you think that's an issue we should, as a community, be worried about because we have less data than the tech companies building large language models?
Well, I think it depends. It depends on how you're framing the problem, because a lot of the large language models are sort of framing it as this sort of self-supervised sort of filling in the gaps, which I think. I mean, Mihai is going to talk when he gives a presentation on the science. He's been working about this sort of self-supervised learning is a great way to scale to larger number of parameters. It's a great way to learn sort of more. Learn large models on smaller data sets, but. Everyone should be aware of this problem, because typically I think we're more likely to be framing things as a fairly simple supervised problem on data that does not feel very big. And in a lot of places, you will be able to make your model overfit. So it's worth knowing that in other domains, we can see behaviors where you find it basically impossible to overfit, but my experiences, I'm sure your experiences have shown that overfitting is something that we need to be really aware of. And so it's more to do with how you're trying to train. Thanks.
I'll pick the closer one. I'll come to you afterwards.
So I'm interested in this gradient descent step. Given the actual nature and or lack of convexity, you're always attaining some sort of local optimum, right? You never find the global optimum. Is that true, or can you have any guarantee that
you have no guarantees? This takes back to the sort of the theory and the practice of sort of yes. And so, I mean, there are ways where you might sort of deliberately increase the size of your gradient step so often this learning rate is adjusted during the learning process. It starts off as a large number, might get to a small number to allow you to find a local minima, and then might deliberately kick you again, giving big steps and trying to make sure that you can jump out of the small minima. But you are left to know with no assumptions. We're training weather forecasting models based on ERA 5 and see that the answers you get for identical configurations can be surprisingly different, sort of equivalent to, do you implement a new model cycle or do you not implement a new model cycle, because they are local minima. So it's another sort of dirty truth.
I was wondering, how flexible are you in defining your cost functions? Can you represent distributions, right? Like for rainfall, a gamma distribution.
If you can write it down in a differentiable form, then anything is there. And in fact, that's again what these sort of frameworks are so good at, is giving you most of the building blocks and letting you just customize what you want to do. So you could take a model off the shelf, an architecture. Mihai's going to talk about architectures, and write down your own cost function. And as long as you can frame it in a way where it can be differentiated through, then it's all game. And I think there's lots of interesting things to play there with exploring different cost functions.
So you can basically combine everything into one cost function.
Yeah. I mean, typically you are
subjectivity, right, or not?
Oh, exactly. So actually, data-driven weather forecasting, which we'll talk about later, it is effectively combining lots of different cost functions, because you need a different cost function to evaluate every point in space for every different variable at every different height. And so you need a way of combining that down. You're trying to reduce down to a single number, and those are going to mean that there are some coefficients to figure out.
Thanks for the talk. Do you have any comments on autoregression in context of overfitting, that the model has actually seen the very similar type of data in training data, what's in the validation data in different space or time, and especially in weather forecasting problems?
I can't decide if I want to answer that now or encourage you to ask that again in the third part, because I think it would be better framed for everyone else in the audience if we. So it's a very good question. I will answer it, but ask it in part 3, please.
Hi, as a beginner in machine learning, I really appreciated your talk. So I was thinking about the parametric assumptions that we make sometimes when we are creating loss functions or cost functions, and what to do when, like, the underlying distribution that we are fitting via MLE, for example, is not really fitting the data, but we are using it in the cost function anyway. Like, it's a very customized problem, but like, for example, I'm working with precipitation right now, and it's not really fitting a gamma distribution, but we are trying to make EGPD work. But what happens if it's like the precipitation is not really governed by any particular distribution, but we are using it in the cost function anyway?
I mean, I mean that's a challenge. You will struggle to fit. I mean, we're going to talk later about there are approaches that don't choose a distribution, sort of like things like diffusion are effectively learning to predict ensemble, so to predict members, to allow you to sample from a distribution without ever having to prescribe that distribution. So I think there are methods that can go beyond needing to a priori pick a distribution and then fit a model to it. So I think those may be suitable. And it's where you've seen, I mean, we're not going to talk for an interest of time about sort of GANs, sort of generative adversarial networks, but these are quite often used or were for an era in precipitation, particularly because they don't require you to assume anything about a distribution, but you have another model that comes and check, does this look like the underlying distribution that I'm trying to attack? Okay, good.
There's one more.
Yes, thank you. I had just a small question about the hyperparameters, and I wonder how would you narrow down the range of the values that you would search for these hyperparameters, because there are a lot of combinations and therefore a lot of computation that you can do, and it can be a bit scary at the beginning.
I mean, I think it's this idea of trying to find some analogy, some similar problem from someone else, and take that as a starting point, and then try and create minimal deviation. So, let's say you're doing a time series problem, like modeling problem. There is a vast literature of people exploring time series problems, sort of try and find an architecture that works well for that, and say, well, that's going to be my starting point, and then allow me, depending on how much computational richness I have, I can then start to deviate from those. I think you find, like in the building weather forecasting models, everyone is starting with the design choices someone else made and then looking to make deviations from them, sort of so that you're not shooting in the blind. To some extent, you do not have to train models to convergence, like to the end, to try and find these minima to get some good understanding. Sort of some of these parameters, if you use a learning rate that's off by several orders of magnitude, your model will either not learn anything at all or will never make progress at all. So some parts of it, or if you make your model too simple, you will see that the loss is not going down. So a certain amount of it doesn't require sort of training to convergence, but can be done sort of with some fast training, maybe on some small data. Typically, actually, you've got the question about overfitting. Some people use sort of overfitting as a good way of testing the parameters, the parameter choice that they have. So they would deliberately shrink down their test data to something that they should be able to learn a perfect model of. I mean, the model wouldn't generalize, so it performed very badly on the validation, but try and find the parameters that allow them to learn that set of data perfectly and use that as a guide. And that, because it's a smaller data set, you could hopefully learn something more quickly. But I have to say, I think mostly it's this idea of going from something that someone else has done is a good starting point.
All right.